Hello and welcome back to another video. This will be Introduction to Riemann Sums. To first start off, we have to understand what are Riemann sums. Well, Riemann sums are a way to find the area underneath a function. Okay? For anybody who doesn't know what a Riemann sum may or may not look like, you'll have a function, and then you'll have a bunch of boxes. This is nothing specific, so don't actually worry about what type this is, but you'll have boxes underneath the function. And this will categorize and tell you how much area is underneath that function. Now, it is a rough estimate, and we'll go over the types of Riemann sums and which ones are usually closer to the actual answer. And then maybe in a future video, we'll discuss how to actually get basically the definite volume and area underneath a function, right? Sorry, not volume, as it's not a 3D object yet, but for a 2D function, how much is underneath that. So let's talk about the types of these graphs. So the types of Riemann sums, there's 4. There's left, right, middle, and trapezoidal. And what do these really mean? These are the starting points of where the boxes underneath the graph will start, right? So for an example, a left Riemann sum. In this example, the left corner of the box will touch the function. So it's going to look something like this. Now, I'm not going to go on forever, or this video will take too long, but you will understand that the left corner will touch. Now, in examples, I'll just go for this, but you'll see that eventually there's going to be some area outside of the function, because that's how left Riemann sums work. Now, this area and this area, these are portions that aren't actually underneath the graph. And now, sometimes these areas will completely cancel each other out, but in most cases they won't, right? So left, right, middle, and trapezoidal are not perfect indications of the area. It just is a rough estimate. Now, right Riemann sums start at the right. Their box starts at the top right corner. Now you can see that the same issue will occur with right Riemann sums, where the area outside will be similar to the area lost because we're not measuring all of the inside. So both are not perfect ways to measure. All of these types are not perfect ways to measure. Now, middle Riemann sum is a little bit different. Where do you think the point will start in the middle Riemann sum? Well, it'll obviously start in the middle. Say we have this being 4 here, and this is 8. Now, we have a Riemann sum. Well, I'll show you the notation for the Riemann sum later, but say we have a middle Riemann sum, just call it n, and we want to break it up into 2 intervals. And we have this interval here, 1 through 8, right? So 2 intervals, 1 to 8, 8 over 2 equals 4. So we know that 4 is going to be one of the endpoints and the start point for one of the Riemann sums. Now we know we have to have 2 Riemann sums spread across an area of 8. And we know that the middle point will be 4. Now, from the interval 1 to 4, we need the midpoint to be in between that. So we need the midpoint of that Riemann sum to be 2. So we're also going to draw in our 2 here and our 6 here. So the middle Riemann sum for this exact thing would look something like this. This box will be lower to hit on this point here. Actually, I could just undo that. Let's do that. So it will be right there. Okay? And then we'll have another one in which the middle point will have to hit 6. So we'll have one going here. Now, if you're starting to see a pattern, it's good. We have area and area outside and inside that's being missed, but over general, the more intervals a Riemann sum is broken up into, the more accurate the area will be. Now, why is this? Well, there will be less above the graph and less error below the graph. Because when you break something up, for instance here, this gets smaller and the error on the outside gets smaller. So there will be less miscalculation and less error the more intervals there are, leading to a more accurate prediction of area underneath the function. Now, let's talk about the last kind, trapezoidal. I'm going to make kind of a big graph so we can comprehend this a bit better. Now, what is a trapezoid? A trapezoid is something that looks like this. All right? And for trapezoids, the graph may look something like you have a point here, and the boxes, they look like trapezoids instead of normal, normal things. So you may have something like this, where you have trapezoids underneath, right? And you may encounter like error in these trapezoids, right? But trapezoids are usually regarded as one of the more accurate Riemann sums. So we know that left and right are going to have about the same amount of accuracy. I don't know if I spelled that right. I actually don't care. In the middle, it's going to have slightly more accuracy in most cases than left and right. So plus more accuracy. And then the trapezoid will have the most accuracy. Now, what is the notation for Riemann sums? Okay, so we have different notations for each one. For, let's say the basic format is this. We have, let me make that a bit better. We have A subscript n. This A, it won't be an A, but it will categorize if it's left, right, or middle, or trapezoidal. With A, obviously, a right, which is going to be right, a left for left, an M for middle, and a T for trapezoidal. Now, these are usually uppercase, just keep that in mind. And this N will be the amount of points and splits underneath the area in the interval. So say it was 2, it would be 2 boxes. Now, let's look at a problem with this, shall we? Alright, so we have this question here. Compute the right Riemann sum from the interval 0 to 6 with 3 subintervals. So the interval 0 to 6, here to right here. Now, we know it's a right Riemann, and we recall what that looks like. Something like the right side of the box. This point will touch the line. So it's going to be like that. Sorry. So we can do this. How must we start? So 0 to 6. 6 divided by the 3 subintervals is going to be 2. So we know that each of our intervals will be 2 paces apart. Alright, so let's mark this. 0 to 2, 2 to 4, then 4 to 6. Now we can start drawing our right Riemann. So here, that line is not straight at all. Let's try to make that straighter. Undo, undo, and move this right there. Let's try to make this straighter, shall we? Okay, okay. Wow. Any as such, it doesn't matter. Now we have this 4, 2, 2. I know my lines are very straight. Alright. So now, how do we actually get the area of this curve? Well, we know how to find the area of rectangles and boxes. Obviously, it's length times width. Now, we have 3 here. So we're going to have to add a1 plus a2 plus a3 equals, and it's going to be the right Riemann sum of 3 subintervals. So a1 is going to equal, well, what's this? This is 2, and then how tall is it? It's 4. 2 by 4, and that equals 8. So we know a1 equals 8. Now a2 is also 2 by how tall? This is 1, because we can see over here this would be 1. So 2 by 1, well, that just equals 2. And now a3, we know it's going to be 2 for the width again, but this time we have a height of 3. So 2 by 3, and let's make this 2 by 1 to make it clear. 2 by 3 is 6, so we know that a3 is 6. Now what's the areas of these all added up? It's 16. So that is going to be the right Riemann from 0 to 6 with 3 subintervals. The calculated area will be 16. Now I kind of want to re-go over some basic things, right? Usually when we're given Riemann sums, we're not given a graph. And if we're given a graph, it's super easy, right? But sometimes we're given equations like, say, f of x equals 2x plus 3. Right? Sometimes we're given equations. Now, how can we find this? And say we want to find on the interval 0, 3, and we want to find r6 on 0, 3. Now recall right here. So we need to split 0 to 3 into 6 intervals. We obviously know how to do that. It's just 3 divided by 6. Obviously, this is just 1 over 2, or 0.5. So now we know that each interval is going to be 0.5. And that gives us our x's, right? This is obviously going to give us 0.5 for x values, 1, 1.5, 2, 2.5, 3. Okay, so these are our x values. Sorry if that is a bit close. These are our x values. And once we have x values, it's very easy to find the y values, as f of x, basically is just a replacement for y in most scenarios. So how would we get our y's? Well, we have to plug each individual one of these values into this 2x plus 3. You could do this. It's going to be very tedious and very, very difficult. But there's actually a way to compute these Riemann sums. There's an equation to compute these Riemann sums way easier than what they usually tell you. And that equation differs from left, right, middle, and trapezoidal, but I can tell you them right now. So for left, right, and middle Riemann sums, it's very simple. You can get this change in x value, and then you must multiply it by the sum of the f of x's values. So we have f of x is here. Now, how can we do this in terms of the equation that we were presented with? Well, let's calculate the change in x. So we know that change in x is final minus initial. And for our interval, we have 3 minus 0. Now, our change in x is going to equal change in x. And we know that it has to be over the subintervals. So we have 6. So we know that the change in x is going to equal 0.5, or also just 1 over 2, but we can stick with 0.5. So this equation we can work through now. We have 0.5. So we have 0.5 for change in x. Now we just need all of the f of x values for these corresponding points. So we can do that. We can do 5, and then we have to do f of 0.5. But, sorry, I actually almost forgot the one caveat, is in these sums, if we're doing right Riemanns, we know that we're missing one of the points. We don't start directly at 0, comma, whatever the x value would be. And sorry, there's also a 0 here. There's a 0 here. Now, we don't start at this x value because we're missing it. It's not a left Riemann sum, so we can't start at this 0 value. For example, let me draw this. It'll probably make more sense. We have a right Riemann sum. It can't start here, especially on the interval 0, 3. It has to start here, further away from the starting point. So we cannot have a point 0, comma, whatever y value, as the Riemann sum wouldn't make sense for that. We can do this for left, but we can't do this for right. And now keep in mind, for left, we can't include the point 3, comma, y because of this same problem. It goes past the interval, right? So just keep this in mind when calculating. And I did forget this 0 here, which was a pretty bad mistake, but now it doesn't matter. So let's calculate each one without this value, since we're doing right Riemann sum. If we were doing left Riemann sum, we wouldn't do the 3 value. So f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 plus f of 3. Now, what actually is this? Let's calculate that right now. It's 0.5 times, well, we know that, skipping the 0, 0.5 times 2, that's 1, plus 3, that's 4. So we have 4 plus, and then 1 times 2 plus 3, that's going to be 5 plus, and I think I'm seeing a pattern. I think it's going to be 6. then 7, then 8, and then 9. Now, if you don't believe my calculations, you can do this yourself and see what you wind up with. But I get this. And then these numbers added together, I believe, are 39. 0.5 times 39. Well, what is 0.5 times 39? 0.5 times 39 is 19.5. Sorry for the cut there. I did have to whip out my calculator. It's probably fairly easy considering that it's very close to 40 and you could just, calculate it. But it's 19.5 and that equals our Riemann 6. Now, say we didn't want to do Riemann 6. Say instead we wanted to do like a left Riemann, sorry, not a Riemann 6, but a right Riemann 6. Say we wanted to do a left Riemann 6. Well, so we know we want a left Riemann 6, and we know that the change in x is going to be the same, right? This is going to be 6 right here, and then change in x equals 0.5 again. And then we do 0.5 times the sum of the functions f(x)'s. Now remember, with left Riemann, since it looks like this and this corner touches, we have to exclude this last value. So we can't include the 3 value here. And we also have to keep in mind that now we do have to calculate this 0 value. So f of 0, well, that's just 3 plus 4. Sorry, it's 3. And then we're going to continue. 0.5 is plus 4. 1 is 5. 1.5 is 6. 2 is 7. 2.5 is 8. Now this equals, sorry, this is supposed to be a plus. This will equal, well, this is 10. This is 10. So we have 20, 28, 23. So we have 23 times 0.5, which should equal, to my calculations, 23 divided in half. Well, we know half of 20 is 10. Sorry, is it 23? It's 33. I'm being silly, obviously, because we have 20 with the 6 and the 4, and then 3 and the 7, and then the 8 and the 5, right? This is going to equal, well, we know 30 divided by 2, that's going to be 15, so we have 1.3 divided by we have 3 divided in half, which is 1.5. 1.5 plus 15, that's 16.5, and this equals our left 6. Now, you can do the same thing for the middle. Now, keep in mind, though, it's going to be kind of different, right? So let's go back. For the middle, it's the same equation once more, of course, but instead of, since the point is in the middle, we're going to have to figure out what the midpoints are. So the f of the midpoints, instead of the, well, it's still an x value, but you understand that this is the midpoint, not any of these sort of intervals. Say we wanted to do middle Riemann and say, what could we do? We could do middle Riemann, what do we want to do? We could do 6 once more, I guess. However, it's going to be very difficult. Let's do 3 just to make it easier. So let's find the average. Obviously, it's going to be 3 minus 0 over 3. This gives us a mean of just, 1. So I guess that works, which is great. We have 1 as a mean, and we have to find the midpoints on 3. So what are our x values even going to be here? Well, we have a midpoint value. Since there's 3 intervals, 3 divided by 3, that gives us 1 for each. So they're going to be spaced out 1, right? They're going to be like this. Sorry. The we know that the midpoints are the middle, and it's spaced out 3. So this is going to be 3. This is going to be 2, so this middle point will be 2. And this will be the 0. So we have to find the midpoints. One of our x values for this are just going to be, well, we already have the 2, but what's between 0 and 2? It's just 1. Between 1 and 2, between, excuse me, what is happening? Between 0 and we have 3 of them, so it's going to be 0, 1, then it's going to be 1 to 2, and then 2 to 3. So it's actually going to look something like this. Right. Now what's in between 2 and 3? 2.5. What's in between 1 and 2? 1.5. And what's in between 0 and 1.5? And now we don't have to get any points because all of our points are going to be in the interval, obviously. So these are our x values. Now let's find our y values corresponding to this. 2x plus 3. So we have the 2.5 times 2.5 is just going to be that 8 value, I'm pretty sure. So 8 plus this 1.5, which is going to be 3 plus 3, which is 6, plus 0.5, which will just be 1 plus 3, which is 4. And then we times this by the change in x, which will just be 1. And then we have here 18. And now, coincidentally, I'm pretty sure that this is the exact value as well. So this equals the integral. I like to draw my integrals actually as an s. And then we'll go into integral notation later for the function 2x plus 3, which is very coincidental. But yeah, let's go back. We can do trapezoidal now just to demonstrate it. Now, in terms of trapezoidal Riemann sums, this one is one of the more complicated versions, but the equation is going to be change in x over 2 times the sum, once again, of the functions. But there's a caveat to this. And the caveat is that you're going to have to double. There's going to be, say you had 4 values, right? You're going to have to double the inside ones. So 2 times whatever value that is. It'll make more sense when I show you how to do it, but it's gonna double. So let's first grab our intervals. Now trapezoids, they work like this. All right, and on the interval 0, 3, let's just find our change in x. Say we want the trapezoidal sum 3. So the trapezoidal Riemann sum 3 is going to be 3 minus 0 over 3 equals 1, and then we have 1 over 2 times our sums of functions. What are the x values going to be? Well, we have x values for 0. We need y values for 0, 1, 2, and 3, because this is basically where our trapezoids are going to be, right? So let's find these x values, because we know that the change in x is 1, so we create an interval for each one on this interval here. So where are our y values going to be? Well, let's calculate it. Y of 0 is just 3. Now, here's the caveat. 1, we have to do 2 times f of 1. Well, f of 1, that's 5. Now, we have to do another one because we're still in between these last 2 digits. 2, that's 4 plus 5, 6, 7. So it's going to be 7. Then we have to add that once again to just the normal one. So f of 3 is going to be 6 plus 3, which is just going to be 9. Now, what this results in is 0.5 times, well, let's do it. This is 10, this is 3, this is 14, and then this is 9. So this is going to equal, we have 20 here, 24, 24, plus 3, 4, 5, 6, 7, 27, plus 9, which is just going to equal the value 36. And then what is 36 divided by 2? Well, it's just, this is 36. Now, what is 0.5 times 36? This is 18. So this is the exact sum we got from T3 and M3. And this is also the exact value. So that's how you can computate Riemann sums with equations. The trapezoidal Riemann sum's a bit more complicated, but I hope my explanation of it was adequate. In the next video, we will be talking about probably more calculus stuff, but yeah, hope to see you then. Thank you.